Welcome back to the lecture on rolling element bearings, to part 2. And here I will start to talk about the materials that are commonly found in rolling element bearings. Now, the most common material is steel, and it typically is a ball bearing steel with a designation AISI 52100, also known as a 100 chromium 6 steel. It's a high purity steel which is heat treated to obtain a very high hardness, typically around 800-900 Vickers. There are also hybrid bearings, where the rings or the races of the bearing is made from steel, but the rolling elements are made from, for example, a bearing grade silicon nitride. Now, since you have a hard ceramic as the rolling elements, this can be considered to heal damages on the bearing rings, because there is such a large hardness difference. The softer material, in this case the steel, will deform as the rolling elements are passing over a potential damage on the surface, and can sort of deform and flatten out that damage to heal the bearing. Typically you don't have any adhesive wear between the ceramic material and the steel, since these are not very much attracted to each other as steel versus steel is. There are also coated bearings where, for instance, the rolling elements are coated with a diamond-like carbon coating, DLC coating, mainly to reduce adhesive wear and reduce frictional losses in the bearing. When it comes to lubrication, all rolling element bearings are of course lubricated to minimize wear of the bearing and to minimize friction also of the bearing. The lubrication regime is what is known as EHL, or elasto-hydrodynamic lubrication. You have already taken lectures on that earlier in this course and learned about that. So you know that there is a lubricating film that separates the surfaces, and the surface I'm talking about here is the rolling element and the race. And since these are separated by a very thin oil film, that enables very low wear rates also of the bearing. When it comes to the type of lubricant, grease definitely dominates. Some figures indicate more than 90% of the bearings are actually grease lubricated. This provides a lubricated for life system where you apply the lubricant into the bearing and you seal the bearing, and then you have the lubricant in the bearing. The grease also enables some sealing capacity, meaning that it can keep contaminants out from the bearing and it doesn't enter into the contact between the rolling elements and the races. You may also use a so-called central grease lubrication system, where you can distribute grease to several bearings in complex machinery from a central let's say grease system, where you pump out the grease from a central reservoir. When it comes to oils, typically the oil is designed or selected for other components in the system. For instance, the gears or some other component where the bearings are situated very close to that component. So in that case, the bearings are lubricated using the oil that is intended or designed for another component in the system. Regarding grease lubrication, now the advantages of having grease lubrication is, for one, it stays in place. If you put it there, it will stay where you put it, and then sort of gradually release the lubricant into the contact where it's required. As I mentioned, it also has a sealing capacity, so it can keep contaminants and particles out from entering the contact between the rolling element and the race. It will continuously replenish the lubricated contact with the right amount of lubricant, since you bleed out the oil phase from the grease into the contact where it's required. as I mentioned, you also have a live lubrication approach where you don't need to re-grease the system. You just apply it there, you seal it, and that will last for the life of the bearing. And speaking of seals, the typical seal that you will find in a rolling element bearing is a radial lip seal, which is the green part indicated here to the side. Here you have the rolling element, this is the grease, and here you have the radial lip seal. And the radial lip seal seals towards this surface right here and here. And it is designed to keep the lubricant in place in the bearing or in some other system where it may be used, and to keep contaminants out from entering the bearing. And this is done through the rather complex geometry of the bearing, proper selection of materials, surface roughnesses, and design of the seal itself. And this all together will result in a system that can seal off contaminants on the outside and keep the lubricant in the bearing, for instance. If we then look at the surface roughness of the bearing, you know, any engineering surface is never perfectly smooth. There's always some roughness. And a typical roughness of a raceway, for instance, in a rolling element bearing, the roughness height is typically greater than the minimum film thickness. For instance, indicated here in the second bullet, the RA value, the average surface roughness is of the raceway, is typically in the range 300 to 500 nanometers. But due to the high pressure that we get from the small contact area and the load acting on the rolling element versus the race, and the complex interaction that you have between the lubricant and the surface, that will actually flatten out the roughness and enable the film buildup and separation of the surfaces. And the roughness also plays a role when it comes to contact pressure and subsurface stresses. Here you see three examples where you have a smooth surface to the left, indicating the pressure distribution, and you see the stress concentration in the subsurface here. As you can see, you get a very nice symmetrical distribution of the stresses. Now, if you have a rough surface, on the other hand, you will get a rather different behavior where you have concentrated stresses in the subsurface, and you also shift the position, as you can see, compared to the smooth surface. And if you also add a slip, meaning that you have some sliding between the components and not just pure rolling, you can then also shift this stress distribution in the subsurface to some direction depending on the direction of motion. So these are important parameters to keep in mind when you, for instance, design bearings or you deal with bearing failures to backtrack what has can have caused the failure that you observe. Speaking of subsurface stresses, then, when we talk about subsurface stresses, that means the stress that will occur in the material and not at the surface. And the stress maximum will occur close to the surface at the pressure spikes, somewhere in this region. And if you increase the sliding in the bearing, you will also increase the stress maximum. And increasing the EHL friction will increase the stress closer to the surface. And this becomes important when we will be discussing wear and failure of the bearings, since if the stress maximum coincides with some dislocation or some other impurity in the material, you can have crack propagation and nucleation and propagation of cracks. Now we'll be talking about friction in rolling element bearings, and there are two main friction mechanisms in rolling element bearings. We have what is known as microslip and elastic hysteresis. And if you look at microslip to start with, there is always some percentage of sliding in the major part of the contact. Now what we see here is the contact ellipse, meaning the contact between the rolling element, in this case the ball, and the groove in the raceway. That becomes an elliptical contact. And as you can see, In some part of the contact, the ball will actually have a reverse velocity, and other parts of the contact it will have a forward velocity, and there will be some narrow bands where you will have pure rolling. Now this will give rise to certain amount of slip, which is what is known as rolling friction. It can be exemplified by the wheel principle. For instance, in the figure, if you have no relative movement, you will also have no friction. But as soon as you have for instance, a varying radius in the contact, you will encounter some slip. And if the radius varies due to deformation, you may encounter partial sliding, which consumes a part of the energy and is the rolling friction that occurs. When we talk about elastic hysteresis, if you picture a solid body rolling on another solid body, the material in front of the contact will be deformed, and it will be recovered at the back of the contact. If you look at one point, when the ball has passed that point, it will recover just behind. But a small fraction of the energy that goes into deforming the material in front of the contact will not be recovered at the back of the contact. And this consumes part of the energy that you put in, and is one reason for the friction that occurs. Now this will all depend on the stress level in the system, and it also depends on the hardness of the materials that are involved. So the harder material will have less hysteresis effects. So the rolling friction in a rolling element bearing is very small, but there's also some amount of sliding friction that you can typically found in the following places. You have it between the rolling element and the race. As we've been discussing, there's not 100% rolling, there's always some portion of sliding. You can also encounter it in the cage, between the rolling element and the cage. You may also find it if you don't have a cage and just free rolling elements. You may encounter it between rolling elements, and also where the seal is in contact with, for instance, the race. There you may have sliding friction, which contributes to the losses in the system. And by that, I thank you for listening to the second part of this lecture, and I hope you'll enjoy the third part.